I'm a professor of metallurgy here at MIT, so what I'm really interested in is the design and production of next-generation metals. I tend to focus on metals that are for structural applications or load-bearing applications, where they're going to experience stresses in service, and we want them to experience ever higher stresses, ever more extreme conditions, and we want to do so with lower and lower weight, for example. The way to think about designing a new metal is to think about it in the context of the metallurgical industry, which is very old and it has a lot of historical development built into it. The metallurgical industry grew up in the 30s and 40s and subsequently, and by and large, when the industry underwent that scaling, it did so with a focus on producing a lot of material as cheaply as possible, and the quality of the material was sort of something that developed as an afterthought. And so the progression for the past 80 to 100 years has been to add more detail, add more science in the construction of the internal structure of the metal. So, for example, improving the chemistry gradually every year is an ongoing theme in metallurgical research. And in my work at MIT, what I try to do is build detail into how the atoms are connected together inside a metal. And I would like to optimize the way that we put those atoms together to eke out the very best set of properties that the metal can give us. One of the themes of my research is to focus on designing internal atomic features of the metal which have been underappreciated by the industry in years past. One great example of that is grain boundaries, what we call the grain boundaries in a metal. Most metals, when you cut them open, are composed of many individual crystals. So imagine, a few different crystals and you pack a bunch of them together to make a bulk piece of metal. Well, everywhere you take two metal grains and you put them together, you've created an interface between two crystals, and they can be misoriented so the atoms don't line up perfectly at that interface. And that turns out to be a very small fraction of the atoms that are sitting at those interfaces, but they can have profound impacts on the properties of the metal. In fact, most of the properties we care about, things like strength, wear resistance, corrosion performance, and various other properties, are in many cases dominated by that small number of atoms sitting at the interfaces between the crystal grains. What I try to do in my work is engineer those interfaces. We try to control the chemistry of those interfaces, we control the atomic arrangement at those interfaces, and we control the number of those interfaces inside the metal in order to improve the properties and deliver the best possible property. The grain boundaries in metals are so important that what we've found consistently in our research is that there are a lot of properties where the existing metal set is underperforming by some huge amount compared to what it could be if we get all the details right in those interfaces. So most metals that we use every day, they have headroom. They probably have a factor of 2 or sometimes a factor of 5. In some cases, even a factor of 10 improvement in some property we care about. Things like wear resistance and corrosion. These properties can be dramatically improved if we learn to harness the way that those atoms connect at those grain boundaries.